Hello, everyone. This is one of a series of short interviews that I've been conducting at the Bay Area Alignment Workshop, which is run by FAR.AI. Links to what we're discussing, as usual, are in the description. A transcript is, as usual, available at axrp.net. And as usual, if you want to support the podcast, you can do so at patreon.com/axrpodcast. Well, let's continue to the interview. Adrià, thanks for chatting with me.
Thank you for having me, Daniel.
For people who aren't familiar with you, can you say a little bit about yourself, what you do?
Yeah. So my name is Adrià. I work at FAR.AI. Okay. I have been doing machine learning research focused on safety for the last 3 years. And before that, I did a PhD in machine learning. So I've been thinking about this for a while. And my current work is on mechanistic interpretability, and specifically how we can use interpretability to detect what a neural network wants and what it might be scheming towards.
Okay. So before I get into that too much, so we're currently at this alignment workshop being run by FAR.AI. How are you finding the workshop?
It's really great. I have had lots of stimulating conversations, and actually, I think my research will change at least a little bit based on this. So I'm way less sure of what I am doing now, but I still think it makes sense, but I think I need to steer it somewhat. But I will still tell you, what I've been working on.
Sure. Do you think, has the stuff that's sort of changed your mind about, has it just been like chatting with people? Has it been presentations?
Yeah, mostly talking to people. I think like I've been thinking a lot more about what scheming would actually look like and in which conditions it would emerge. And I think, without going too deeply into it now, but maybe later we will, I was thinking of scheming as a thing that requires a lot of careful consideration about what futures might look like, and perhaps like an explicit prediction of what the future will look like under various things the AI could do, and then like thinking of how good they are for the AI. But actually it might be a lot more reactive. So it might just be the AI sees that like the chain of reasoning from I want to do thing X. If I don't show myself to be aligned, I won't be able to do thing X. Therefore, let's do whatever it seems like in the moment to seem aligned. It's not a very long one that requires a lot of careful consideration. So perhaps the mechanisms I was hoping to catch it with won't work.
So wait, before we get into you said you want to do mechanistic interpretability to find scheming. What sorts of things do you mean by scheming?
So specifically, I talking about when an AI that like has internalized some goal, so it's like an agent, like it wants something, is taking actions to get more of that goal that are not that we wouldn't approve of if we knew of, or like if we knew like why it's doing them. So it's like hiding intentions from in this case, developers or users.
Okay. And so that like hiding intentions from developers or users because for a reason. It seems like that can that can encompass just like tons of behavior, right? Or like tons of things you could be thinking about. So maybe you can say just a little bit about how you've just been tackling it in your existing research.
Yes, that's a very good question. So I've been thinking about scheming specifically towards a goal or towards a long-term goal. So the generator here is the AI wants something that can be accomplished better by, say, having more resources, and that's like the reason that we are worried about loss of control. And conversely, if there is no long-term thing that the AI wants and needs more resources for, then maybe we shouldn't be worried about loss of control too much, right? So maybe like this long-term wanting of things is like really the key characteristic that can make AI dangerous in an optimized misalignment kind of way. And so like targeting it seems useful. And so I've been approaching this by coming up with toy models, or at the start they're toys, so they're like progressively less toy, right? But now we're like in fairly early days with this. Coming up with models that like display this kind of long-term wants and behavior that like tries to get the long-term wants, and then like figure out how are they thinking about this, and like by what mechanism are these wants represented, by what mechanism are these translated into action, and like if we can understand that in smaller models, maybe we can understand it in like somewhat larger models, and like
Sure.
quickly move on to like the frontier LLMs and maybe try and understand like if they have a want machinery somewhere, and if they like take actions based on that.
So concretely, like what kinds of models are we have you actually like trained and looked at?
So the models I'm training now are game playing agents. So we've trained this recurrent neural network that plays Sokoban. Sokoban is a puzzle game that requires many. Like the goal of it is there's like a maze-like or like a grid world with some walls and then some boxes and some places where you should push the boxes to, and then you've got to push the boxes on the targets, and then like if you don't put them in the correct sequence, then like it's very easy to get stuck and you can't solve the level anymore. So
because you can only push them, you can't pull them. So if they get in a corner, you can't like get them out.
Yes, that's right. Yes, exactly. In a corner, you can't get them out. You can't push two boxes at a time.
Okay.
So yeah, it has to be only one box, and so like it's like easy to like inadvertently like block your next box with the previous box, or get into a corner and now you can only move in some directions. Like for example, if you get it into a wall, then you can only move along that wall.
Right.
So yes, it's like the geometry of the levels gives you like complicated actions that you may need to take. Right.
Okay.
So we started from the point of view of a 2019 DeepMind paper by Arthur Guez and others called An Investigation of Model Free Planning. So in that paper, they like did the setup that we replicated here. So the setup is they just train a neural network with reinforcement learning. So just by giving it a large positive reward if it solves the level, and then a small negative reward for every step it takes so that it goes quickly. So they just train it to like play this game, and it like plays decently well on a bunch of random levels that they generate. And then they found that if you give this neural network more time to think at the start, then it is better able to solve these levels. So 5% of levels that it previously was not able to solve, now it solves.
And sorry, when you say more time to think at the start, like...
Yeah, in this case, this is analogous to giving language models chain of thought.
Okay.
The specific mechanism is the recurrent neural network has a latent state that it brings from one time step to the next. So they just process the initial input, like the image of like the puzzle, how it's set up at the first step, just many times.
Okay. So that is this setup that you're replicating. And what do you do with that?
So we got that, and then so we've been poking at it in various ways. Some of the ways were about trying to better understand, like in what circumstances does like more thinking time help solve the levels, or like why does this happen from a behavioral point of view, like what happens to the levels. So I slightly misspoke earlier. I said 5% of levels that were not solved are now solved. That's not actually true. It like 5% more levels get solved.
Okay.
But some of the ones that were solved before now are not, and some of the ones that were not solved before now are, right? Okay. So these like don't cancel out. So it ends up being a net gain. But so we looked at a bunch of these kind of levels, and then like we looked at like how the neural network seemed to behave naturally. Like why might it have this capability to generalize to just if you give it more time, like perform better, right? So the original impetus there was like maybe because you give it more time to think and then it does better, it's doing some iterative algorithm on the inside that can use more computation to like maybe consider more possible solutions and then see if one of them is the good one. Yeah, so the things we found there were pretty interesting for a model this small. So it seems that the neural network has learned a meta strategy just in training of when it needs more time to think because a level is complicated, just like taking time to think. And the way it takes time to think is just it like paces around the level. So this without pushing any boxes. So this does not change the game state in an irreversible way, but it just gives more processing time to the network. So we found like many instances of this of like when the neural network like paces around, we like measured this as to with the proxy of how often does it end up in a state that it previously was in. So like it must have moved in some direction, then came back. And this happens overwhelmingly at the beginning of the level. So you might think that like it's like using this to like plan out the whole level, how it's going to do it, and then it's going to do it. And also, if we substitute these cycle steps by just processing the current input without taking any action, which is, again, out of distribution from training because it always has to take an action, then these cycles disappear in the next few seconds. So you can substitute for the cycles with just thinking time. So perhaps the thinking time is like the main reason that the cycles are there.
Yeah, so that's interesting because so if I think about like stories of AI being scary, right? It's like AI gaining resources, and like one of the resources AIs can gain is like cognitive resources, just like time to think. And
that's a good point.
I'm not aware of like you can have these grid worlds where like an AI has to get money in order to do a thing, and you can like use reinforcement learning to train the AI to get the money. I'm not aware of previous work of showing just reinforcement learning on neural networks resulting in networks learning to give themselves more time to think about stuff. Is there previous work showing this, or?
I actually don't know. I don't know of any either. I suppose we, like the literature research we did, mostly found things like architectures that explicitly try to train in variable amounts of thinking time. So there's like,
and
I believe the neural Turing machine.
Didn't AlphaGo do this to some degree?
Like getting more time to think.
Or in the Lisa Doll games, it didn't have a constant time for each move. So
yeah, I mean, maybe that was pre-programmed after the fact of like search until you get you get enough value, or you get a move that like puts the probability of winning to a high enough amount. I don't actually know. I really think I should look this up now. Yeah.
Okay,
this was not the main focus of the work, so I didn't claim that this was novel or anything. I was like, okay, this is an interesting behavior of this neural network.
Okay. So what was the main focus of the work?
Yeah, the main focus is like train this neural network, and now we have a model of, or like this is evidence that it's like internally like it really has this goal, and it's like perhaps like thinking about how to go towards it. The goal was like, okay, now we can use this as a model organism to study planning and long-term goals in neural networks. And this is a useful model organism to start with because it is very small. It has only 1.29 million parameters, which is much, much smaller than any LLMs. But it still displays this interesting goal-directed behavior, right? So maybe we have a hope of just completely reverse engineering it with current interpretability techniques, and now we know what planning looks like in neural networks when it's learned naturally, and maybe we can use this as like a way to guide our hypotheses for like how larger models might do it. And we took some initial steps in this direction with the help of a team of students at Cambridge as well, including Thomas Bush is the main author. So I advised this a little bit. So they trained probes that could like predict the future actions of this neural network many steps in advance by very simple linear probes that are only trained on like individual pixels, so to say, of the neural network's hidden state, because the hidden state has the same geometry as the input. Yeah, so they can train these, and we also replicated this. We can also train these probes that predict the actions many steps in advance, and then some of these are causal in the sense that if you change the plan that is laid out by so these probes give you like a set of arrows, let's say on the game state, that says like the agent is going to move over this trajectory, or the boxes will move in this trajectory, and this one will go here, that one will go here, that one will go here. So we can also write to this, and then that actually alters the trajectory that the agent takes. So we can put a completely new plan on the hidden state of the neural network, and then it will execute it, right? Which leads us to believe that it really does, like the way in which it comes up with actions really is coming up with these plans first and then executing them.
Okay, so this actually sounds kind of similar to this work that Alex Turner has done on like activation steering.
The mazes and the cheese.
The mazes and the cheese, yeah.
Yes.
And interestingly, I think Alex's interpretations is that agents are like a bit more, without putting words in his mouth, right? This is my interpretation of his interpretation, but I think he thinks that this shows that agents are kind of like a bit more, they have these shards, right? And they have this like, oh, I want to find the cheese shard versus, oh, I don't want to find the cheese shard. And like whichever shard is activating stronger.
It's the one that determines the behavior now.
Yeah, I think he has a relatively like non-unitary planning interpretation of those results.
Yeah.
I'm wondering like, it seems like you have different interpretation of yours. Do you think it's because like there's an important difference between the results, or?
That's a good question. So initially for this project, we also targeted, I think there's some difference. Here's the difference I think there is. Initially for this project, we also targeted maze-solving neural networks.
Yep.
We trained a specific kind of algorithmic recurrent network that a NeurIPS paper by Arpit Bansal, I think it is. Okay. I can give the citation later. Came up with, and then like we looked at how it solved mazes, and it was a very simple algorithm that could be said to be planning, but like does not generalize very much. And like the algorithm was dead-end filling. You can look it up on Wikipedia. It's like a way to solve simple mazes, which are those that don't have cycles. I think those also the mazes that Alex's work used. And like it just works by like you start with your maze as a 2-color image. Let's say it's like black and white, and then like the walls are white, and then like the spaces where you can go are like blank. And then you can, the walls are black, and then the spaces are white. And then you for every square of the maze, you see if it has 3 walls next to it, like adjacent to it. And then if so, you also color it black.
Right.
And then like you can do this, and then you can see the hallways of the maze fill up, and then until like only the path from goal to end, for agent to goal is left, right? And that's what we observed this neural network doing very clearly. And I think this is an interesting planning algorithm, but it's like the state space of this is small enough that it fits completely in the activation of the neural network. So it's a planning algorithm that only very specifically works for this problem. And I thought that perhaps a more complicated environment where the state space is much larger and doesn't completely fit in the activations of the neural network, because here the neural network has an activation for every location in the maze, and then the states are also just locations in the mazes, right? Because there's only one agent, so it's just like the XY position. So it could like perfectly represent this and think about all the possible states and then plan. So I think that plus the fact that you can also just kind of go up and right and just kind of get to the cheese, and like if you get it somewhat wrong, you can correct it. Like makes it so that the neural network is less strongly selected to be able to do this like long-term planning. And also the long-term the planning that you might find like uses a lot less machinery and would be less generalizable. So I think like there's a big difference in the environment here. And then I guess the other thing I would say though is I do think his theory is broadly right, or maybe more right than wrong in that like I do think it's highly likely that neural networks that you actually train are not just one coherent agent that only wants to maximize this one thing, but like it might have like other mechanisms in there, such as like, oh, I kind of just like going right, or oh, I like kind of like this other goal, or and then like also those might play a role. And I think we might find this in this agent, but I think we selected it pretty strongly towards having this one goal of solving this level, and the levels are solved with planning, so it probably does that a whole bunch.
So you mentioned like your paper, a paper by some Cambridge people. What are the names of these papers so that people can look them up?
Yeah, so the Cambridge one isn't published yet,
okay.
But we will soon. But the main author is Thomas Bush, and the title is something like an example of planning in model-free reinforcement learning. Okay. I will have to look this up and send it to you.
Hopefully that's enough for people to Google it.
Yeah. Thomas Bush is and then like our paper is called Planning in a Recurrent Neural Network that Plays Sokoban.
And so going back up the stack a little bit, I guess the reason you were interested in this work is because it sounded like you were interested in understanding agents that were sort of scheming. They're deceptively aligned. They're
Yeah.
like trying to, deceive you and like do some tricky stuff in order to achieve some goal.
Yeah.
And that's why you're studying sort of goal orientation and how it gets implemented.
That's right.
And you mentioned that you had some reservations about that approach.
Yes.
Which I understood to be something like maybe it doesn't take tons of planning to do this sort of scheming behavior.
Yeah. Maybe you don't need to have a goal that you explicitly evaluate. You explicitly think of futures. Yeah, I think you're broadly right. I just wanted to expand a bit.
So you mentioned, so I guess there are like two types of scheming behavior, right? So there's one type, which is you are being trained and somehow you're being trained. And so you're like, okay, I'm just going to play along because like I can't really do anything else. Nothing else is particularly useful right now. That seems like it is not super cognitively complex, right?
Yeah.
But then there's a second thing, which is like, you're an AI, you finish being trained, you're being deployed, but like, I don't know, there are humans around, they don't want you to, execute your super devious plans, so you've somehow got to get around them. And I might think that actually maybe it does need a lot of planning to execute the actually like do nasty stuff part.
Right. That's a good point. Yeah, like if the safeguards are complicated enough and there's like many things that need to go right, then it would perhaps need a lot of planning. I guess I guess I agree with this. Maybe the takeaway here is more that my initial hypothesis as to what planning would look like is wrong,
Right.
rather than like studying planning is not useful.
Okay. What was the initial hypothesis?
Yeah, so I had this model of like, okay, the reason that we can get at planning on neural networks, even if we don't solve all of interpretability, is that planning needs. Okay, I say this now, but I'm not sure I entirely believe it. But for a second, let's put this hat on. So planning needs, exactly. Planning needs a mechanism that thinks about possible outcomes or like possible like ways that the world can go from now on. So I guess you need a world model, right? But I'm also abstracting over this. I'm just saying like, okay, there's just going to be like several possible futures depending on what I do. And like, I'm going to think about a bunch of possible things I might do. And then like, what will the world look like in a while? And then the neural network or like the planning algorithm would like evaluate all of these possible outcomes according to some internal criterion, which is basically how much do I like these worlds that we end up in. And then it would basically look at all the evaluations and then pick the best one and then execute that, right? And so I was like, okay, like we might not understand what's the abstract representation of the future outcomes. That seems complicated, especially if the agent is very intelligent. We might also not understand like exactly how does it get translated into an evaluation. Like it might have lots of like intuitive things and like we might not know what each thing represents. But what we can definitely see, even if we can't do interpretability on most of the everything else, we can see that there's a number at the end that is somewhere in the activations of the neural network.
Yeah.
And there's like a bunch of these. And the best one gets picked, and that is what gets executed, right? So if we would find like this computational signature of this mechanism which like picks the best number out of many, and that determines the action, that is a planning-like thing that would be happening. And I think like this will happen also in a bunch of other circumstances, but like perhaps we can just catalog the, I don't know, thousands of these instances in the neural network, and if they all coherently do something, maybe we like would know like when the neural network is expecting to get a big reward, or maybe we would be able to like ablate these to zero to like prevent any long-term goals from happening.
Although I guess like just having a bunch of actions that you score doesn't say that the goal is long term, right? Like if I'm like, oh, I really like to wave my left arm, I'm going to consider actions that I'm going to take, and which one of them involves waving my left arm, I'm going to do plus 1,000 to that, and I'm going to pick that action like that.
That's right. Yeah.
That would also
Yeah, I guess my intuition here is also that actions that are, or like goals that are fairly short term will be more efficiently expressed as like kind of cached skills or something, or like things the neural network can access, or like you're not thinking explicitly about which muscles you're moving when you're raising your left arm.
Yeah.
So that kind of cognition.
Well, don't presume things about how I think about my muscles, please.
Okay.
No,
I don't know what it's like to be Daniel Phelan.
Most of the time when I'm lifting my left arm, I'm not explicitly thinking about muscles.
But
like,
sometimes
from time to time, it's fun. Yeah.
Yeah. Or like I suppose if you're trying to gain a new skill of like exactly how to move your left arm, like I don't know if you do dancing, then you might have some like technique that you need to move your arm explicitly in a particular way you haven't done before, and
then I would normally not think about muscle contractions, I guess.
Right.
I don't know. I guess you'd visualize the thing. I think the thing where I would think about muscle contractions is maybe in like a weightlifting context.
Good point. Or physical therapy.
Yeah. Sorry, you were saying something and then
Brief
I brought a
but
divergence.
fun aside. No. I think I was finished with my point, which is that, I just said like most of the time, like short-term goals wouldn't require all this explicit outcome planning and would just use like this other mechanism. And so maybe we can, and we would also get some short-term goals there. I was hoping it would be less, or maybe we would be able to tell them apart in some way. Or maybe, I guess I also hope that, okay, now that we have located these goals, maybe we can like trace them backwards a little bit, like, what in the neural network produces this evaluation, and then maybe we can understand a little bit about that. Even if we don't understand it perfectly, we can like get some broad strokes of what it is, and then like, and then like it's difficult for the neural network to modify this. So it even if it's a very intelligent agent, it like wouldn't necessarily be able to like fool our best classifiers. By like changing the way that its internal brain is structured. That seems pretty difficult.
Okay. Cool. Well, we're about out of time. I want to give you time to enjoy the rest of the workshop. Thanks very much for chatting with me.
Thank you very much for having me.
This episode was edited by Kate Brunotz, and Amber Dornace helped with transcription. The opening and closing themes are by Jack Garrett. Financial support for this episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeyev. To read a transcript of the episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.